All right, so let's get started. So this is just another example, and this is not any new material. So the intent of today is to give you, to get you as best prepared for the test as possible. So I thought it would be worthwhile to do another root locus one with a lot of detail and also working out, sort of all the basics. So we'll jump back and forth between whiteboard and this problem. So the one thing, and I haven't mentioned this, and I apologize for not mentioning this, but this test is going to focus on two things, and both of those things use the open loop transfer function, right? Steady state error, because a lot of people have had issues on the steady state error one because they were using a closed loop transfer function. Steady state error, as well as the root locus, use the open loop transfer function. So ESS and root locus use the open loop transfer function. And if you can't remember, the open loop transfer function is just equal to G times H. Okay. Do not do the closed loop transfer function, which is G over 1 plus GH. Two very different animals. Now, the steady state error one makes a lot of sense because when I look at my steady state error, I actually literally open the feedback loop. And then what I'm looking at is the error. It's the difference between the input and this value here. So I'm only going to use G and H because that's the transfer function. To go from this point back to this point, it looks just like a feed forward gain where it's G times H. In the root locus is slightly different because I'm using a controller that has a variable K. And this is my value of H, my summing junction, my plus minus here. And now I'm using at first glance, it looks like I'm using the closed loop transfer function because what I do is G or K times G plus 1 times K GH. But K is going from 0 to infinity. When K equals 0, let me expand that a little bit. So we have K, the denominator, sorry, not the denominator, the numerator over the denominator, all over 1 plus K times the numerator over the denominator times the H numerator over the denominator. And then when I put that under a common denominator, I get Gn over Gd all over Gd Hd plus K times Gn Hn all over Gd Hd. I know when I invert and multiply, this is going to get moved to the top and it's going to cancel out those GDs. So all I'm going to be left with is an HD up here. So the roots of this particular equation, which is my characteristic equation, are going to determine the response. So I have GD, HD, and that's denominator, plus K, GN, HN, right? Well, what do you know? These are just GH. There's no closed loop. It's the open loop transfer function that I'm looking at here. So that's why I use the open loop transfer function for root locus, because when K is equal to 0, that determines my roots. When K is equal to a really large number, those determine my roots. So there's no 1 plus anymore. There's no G, it's just GH. All right. So that's why we're focusing on that. Okay. So that's the first thing I wanted to state. The next thing is, if I look at this, I want to go ahead and I want to solve the root locus for this problem. So the very first thing I do is write what is G times H. So G times H should be K over S times S plus 2 times S plus 4, which is equal to K times S cubed plus, let's see, that's 6S squared plus 8S, right? I don't care what the system type is, even though this is a type 1 system, because the system type is only applicable to the fact that it is a steady state error. So the very first thing we do, this is what I always suggest for root locus, is step one. Draw the real axis, finite poles and zeros, and connect RL on the real axis. So my plot starts out like this. I have no zeros. I only have poles. So I have one over here. I have one over here. And I have one over here. Okay. So that's all the finite poles and zeros. Then I label them 1, 2, 3. And I know I have a root locus that lives over here. And it starts at a pole and ends at a 0. These are both poles. So I'm moving away from the real axis there. And over here, I only have one root loci. So I don't even need to know, but I know that this is going to approach a 0 at s equals infinity. Over here, I can see that I haven't terminated. So I'm going to have to approach a 0 or an infinite 0 at s equals infinity. So I've got two of those. So the very first thing I need to know is I'm going to have to calculate my theta, my asymptote angles. Okay, so this is what I need. My asymptote angles, I need the location of those asymptotes, where they terminate, right? Where they exit. That's the first thing. Then I look over here, and because I have to leave the real axis, I need my breakaway point. Okay. And those are the three things. I can just look at that and tell you that I need to calculate those. What I don't know is if I need to calculate any more, like, are there any j omega axis crossings? I don't have any angles of arrival or angle of departure because I'm not leaving any complex conjugate poles or zeros. So there are no angles of approach or angles of departure. Don't need to worry about those. So I know I need to calculate these. I may need to calculate the j omega crossings. It just depends. If my asymptotes make it so that my root locus goes on or crosses the j omega axis, then I would need to calculate those. If not, then I'm good to go. So I'll have to figure out what my sigma sub a is before I'll know for sure if I need to calculate the j omega crossings. Okay? Makes sense a little bit? Just trying to lay it out so we can understand sort of the basics. All right. So I'll calculate my thetas and my sigmas. So I know that I have to calculate my centroids. That's the sum of the poles minus the sum of the zeros divided by the order of the numerator minus the order of the denominator minus the order of the numerator. So where those points leave is, whoops, I can't write on that, is -2. And then now I'm going to go ahead and calculate my asymptotic angles, which is 2 times n minus n times plus or minus 180 divided by n minus m, right? So I have 60, 180, and 300 degrees. I'm glad I have one at 180 because if I look back over here at whiteboard, I know that there has to be an asymptote that approaches that s equals infinity, way over there to the right, correct? So this angle here is 180 degrees. The other two are going to start at -2, which just happens to be here, and they go up and down at 60 degrees. So because they're going and crossing the j omega axis, I know that I have to have points that cross the j omega axis. So yes, I do need to calculate my j omega crossings, which means I need to do a root locus to calculate those. Okay. So I've calculated this one and this one. Now I need to calculate the breakaway points And then I'll calculate the J omega crossings to get a little more refinement, and then I'll just check some points. Okay. So I have my angles. I'm going to calculate my breakaway points by doing my partial derivative. My partial derivative of -1 over my, so negative, it's -1 over GH. So, geez, I can't talk. Actually, no, it's the partial of GH. No, -1 over GH. So I've got my -1 over S squared or S cubed plus 6S squared plus 8S. Derivative of the numerator times the denominator minus the derivative of the denominator minus the numerator gives me, or times the numerator gives me that value. And all I need is this term here because I'm setting that equal to 0. So I'm going to combine that. And what I end up with, this is multiplied by 0. So this is the only term that I have left. 3S squared plus 12S plus 8 equals 0. You can use your calculator to solve for the roots. I just wanted to show you, you can still use the quadratic equation. It works fine. I have -2 plus or minus 1.15. All right, let's go back to the plot. So my sigma sub b, I've got two of them. -2 plus or minus 1.15. I only want the real parts of sigma sub b because I'm leaving the real axis, so I can't have a complex number if I'm on the real axis, correct? So which one is valid? So remember, this is, let's see, this is -2 and -4, the actual points, and this is 0. Is -2 plus 1.15 a point where I break away from the real axis? If you're not sure, that's -3 plus 1.15 and -3 minus 1.15, which is equal to 0.85 negative and minus 4.15. Are those valid? Well, I have one over here. This is minus 4.15 and minus 0.85 is right over here someplace. So I've got two of them. Does that mean I break away at both locations? Think so? If I break away from the real axis, what do I have to have? When I leave the real axis, what do I have to have? Complex conjugates, right? I have to have a plus j and a minus j. How many root loci live here? At minus 4.15. There's only one. So how can I break away from the real axis at minus 4.15? If I need complex conjugate pairs, I'd have to go up and down. But there's only one there. So I either go up or down. I can't go both. Over here, there's two, right? I've got the two arrows. So I have two root loci. So I leave at minus 0.85. That's the only valid breakaway point that exists for this problem. Even though minus 4.15 is a valid Roos locus point, it's not a valid breakaway point.
Just want to make sure I understand it right. So in order to be a valid breakaway point, you need at least two values. So it's one is valid and it's safe on the real.
Yep. So there's sort of two conditions. You need to have two root loci, right? And it has to be on the real axis. If it's a complex number, then it's not on the real axis, so it can't be a breakaway point.
Okay, thank you. It's
hopefully obvious that if it was a point right here, there's no root loci at all, so that one doesn't even count. Okay. So there's the roots, and I guess I got a little more refined. Minus 0.845 is our final answer. So there's the general shape of what it looks like. Now I want to figure out these 2 points, which means I need to do the root locus, the Routh-Hurwitz approach. I think I said root locus. I meant to say Routh-Hurwitz. So Routh-Hurwitz says do the characteristic equation for this, right? So I need 1 plus GH, which is going to be equal to 1 plus K over S cubed plus 6S squared plus 8S. Put that under a common denominator. And I don't care about the denominator here because I know I'm going to invert it and multiply. So now this is my characteristic equation. So I do the Routh-Hurwitz for that. So I have rho S3, S2, S1, S to the 0. So I have 1, 8, 6, K. To get this one, it's negative 1, 6 over K minus 48. And this is 0. Well, actually, let me go ahead and write it out completely just to, so I'm not going too, I'm probably going a little too fast. So this is going to be 168 K, which is equal to, let's see, that's going to be equal to K minus 48, or negative K minus 48 over 6. So K minus 48 has to be less than 0, right? So K has to be greater than or equal to 48 for this to remain a stable system. At this point, we know that this is going to be equal to K. We don't have to do the work. So our Routh-Hurwitz says, if we want this to be a row of zeros, K has to be equal to 48. And then we use this auxiliary equation, 6S squared plus 48 equals 0, right? Tell me if I'm going too fast. That's a row of zeros. Remember, I use our auxiliary equation. I set that equal to 0, and then I solve for the poles, for the roots of this. So S is going to be equal to the square root of 48 over 6, which is the square root of 8, negative 8. So S is going to be equal to plus or minus J square root of 8. Though where this crosses is plus J square root of 8 and minus J square root of 8. Okay. And that's as much information as we can use to draw the root locus. Now, let's use MATLAB. So all I did was I typed in sys is my transfer function, and I pass it the open loop transfer function, right? The GH. I didn't do the closed loop transfer function. Oh, no, I did do the closed loop transfer function, but I didn't include K in there because it's a variable. And here's my root locus plot. And I highlighted the points where it crosses the J omega axis. It's kind of hard to see. And I didn't want to mess with the scale, but this is -4, -2, and 0. But if you look over here, you can see that this is a really small number, right? It's almost 0, plus and minus J 0.82 or square root of 8. I didn't get it exactly. I was close. And so that validates our plot. Let's check a couple points. Will minus 3.5, is that a root locus point? It doesn't look like it's on there, but let's check and see if this is valid. So the first thing we're going to do is we're going to check the angle. Remember, 1 plus K GH has to equal 0, which means K GH has to equal -1, which means the angle of K GH has to equal plus or minus 180, which really means the angle of GH has to equal plus or minus 180 because K is a real number, so it doesn't add any angle. So all we need to do is check to see at GH, plugging in the pole that we think is valid, -3.5. Do we get 180? Well, let's check that over here. Let me erase this out of the way. So here's our equation, our original equation. We plugged in -3.5, and we end up with this. Now we have our angle at -3.5. This is an angle of 0. minus 3.5, hopefully you can see that that's plus or minus 180. Another plus or minus 180. This is a positive number, so it's 0. So I'm adding all the angles in the numerator and subtracting all the angles in the denominator, and I end up with 0. Does 0 equal plus or minus 180? It does not. So minus 3.5 is not valid, which is good because it doesn't show a red or a green line existing there. That's not a valid point. How about a point over here? Minus 5. Let's try minus 5, same approach. So minus 5, I'm just plugging in minus 5 like I did minus 3.5. And here's what I end up with. Now I'm going to go ahead and calculate the angle. 0. This has minus 180, minus 180, minus 180, or plus 180, doesn't matter. So 0, subtracting all those equals minus or plus 180, right? You can say, hey, wait a minute, Paul, what happened? But keep in mind, this is equal to 540. And every 360 degrees, it repeats, right? So this is really equal to 180 degrees, isn't it? Because when you go 360 degrees, you start back at 0. So that's why I just said that's equal to minus 180 or plus 180. But this validates that. And so what we see is that the angle is equal to plus or minus 180. So this is a valid point. So now let's solve for K when we get minus 5. So I'm doing this by hand. So I'm going to plug in the magnitude. I'm going to solve for K. And again, it's magnitude only. So I'm going to do K equals 1 over GH. So I plug in my value of minus 5. And what I end up with is the magnitude of minus 5, minus 3, minus 1 is positive 15. So when K equals 15, I should get a value of minus 5. Go back to MATLAB. And again, I got as close as I could by eyeballing it. And you can see right here, for a gain of 14.7, my pole is minus 4.99. I couldn't get it any finer, but looks pretty close, right? K is almost equal to 15, and the gain is almost equal to, the pole is almost equal to minus 5. So all that stuff checks out. Questions? Everybody bored to tears?
So I have a question, Paul.
Yes, sir.
So my question is about the asymptotes.
Yep.
So I've been trying to work on an example where the degree on the numerator is like twice greater than the one in the denominator, such that when I do
You can't do that because no real world system will ever have the numerator order greater than the denominator.
no, it's twice less. So when we
twice
do
less,
the difference,
okay.
yes, when we do the difference,
Yep.
it's giving like n equals 2.
Yep.
So so I was like kind of confused about finding the asymptotes because of the values of R. So should I just use R equal 1 and that's it?
No, so let's go back to, let's look at, let's see if I can find, whoops. Just bear with me when I find the equation. So I want to make sure we're using the same equations here. So R is equal to 180 times 3, and R is going to be equal to plus or minus 1, then plus or minus 3, all the way up to n minus m, okay? Let's go up one more. So here's your value of R. And n minus m is going to vary between, it's just going to go up. So this R value should never exceed the value of n minus m. And it's always going to be odd. Okay. So R is going to start with 1. Then if you can, if n minus m is 3 or greater, then you're going to plug in 3. And then you can go to 5 if n minus m is 5 or greater, et cetera, et cetera.
All right, so in my case, it's equal to 2. So I should just start by R equal 1.
Exactly. Yep.
All right, yeah.
Because you
thank
can't, your R value can't exceed. And that makes sense, right? Because you can't have more asymptotes than you do infinite zeros, correct?
Yeah, actually,
So you only have, if you have one zero at s equals infinity, you only have one asymptote. Like you said, n minus m is equal to 2. That means you have two zeros at s equals infinity. So I only have to have two asymptotes. So that's why I have the plus or minus 90 here. I don't go to plus or minus 270 because I don't have four asymptotes. Okay.
yes.
Was this helpful at all to go through this? Feel like I get a little bit better understanding? Because somebody had some homework questions on the weekend and they were saying, this is the first homework I was unsure if I got right answers, which would indicate to me that the learning, we haven't learned this stuff quite yet. And I don't know if it's because the math is too intense or it's just a complex topic to grasp. So I kind of wanted to walk through all the steps and then show some of the application to it. Okay. All right, well, let's do,
Hey Paul, I have a quick question.
yes,
So are we like asked to find JAX crossing points and everything like on the exam
you
too?
may need to, yes.
Okay,
If you want to, if you have a case, and this is a case where they did cross the J omega axis, then you would have to do that. Okay,
Okay, yep, thank you.
sure. And here is all our stuff. Steady state error. The way that you solve for steady state error, we did this in lab, figure out the system type. The system type is a number of integrators at s equals 0. Once you know the number of integrators at s equals 0, then you can proceed and use this table to calculate your position constant, your velocity constant, your acceleration constant. Yes, sir.
Okay, so will this table be provided? on
Yes.
the Gemfile?
Yes.
Okay, thank you.
So once you have those constants, or once you know the system type, then you can immediately just say, oh, it's a type 0 system. So if it's a type 0 system, all I need to focus on is this part here. This is where my calculations are all going to be applicable. It's not a type 1 system, so, or type 2, so I don't need that. So for a type 0 system, my K sub P value is a constant, which I determine from here. And my steady state error is 1/1 plus K sub P. This assumes that it has a unit step input. If it is not a unit step, let's say it's a constant times a unit step, let's put a K over there. You multiply the steady state error by K. All right, that doesn't change your error constant, it just changes your steady state. Then your ramp and your parabolic input, your K sub B and K sub A are going to be 0, and your steady state errors for those are going to be infinite. Because of the type 0 system, you have no integrators, and the input is changing too fast for your system to keep up with, so you're going to get infinite error. If you have one integrator, then I'm going to use this next column. Let's see if I can change the pen color. Where is it? Usually I can see that. Here's my edit. It looks a little bit different. Let's see if this edit one, normally you have the pen default up here, but I don't see it here. No. What's that? Is it a big what? This one? We can try it, but this is, I thought this was the signature. Yeah, this is just your sign. Let me try comments. Sometimes a comment one would work. Let's try comments. Try that again. Here we go. It's the comment one, so I can change the color here. It's type 2 system or type 1 system. All we have to do is focus on that. One integrator means I can keep up with a constant input. I can integrate out the error. So there's no error there. And my position constant is infinite. My velocity constant, though, I can keep up. I can actually improve the step, no problem. Parabolic, I can maintain a constant error, but I can't make that go to 0. So that's why I get a little bit of error there. But acceleration, I can't keep up at all. So that's why it's infinity. And then lastly, let's pick, no, that's too close. Let's pick this one. Oops, it changed it. So let's try that again. Type 2, that's what I use. So all you need to do is figure out the system type, how many integrators or poles at S equals 0, and then can I keep up or not keep up? And all the information is revealed. Okay. That's kind of it for steady state errors. Again, I'm just using the open loop transfer function. I said OP, I should have said OL.
Okay, so you use the three equations of the top to define type.
Nope, the system type is determined by looking at GH and how many poles at S equals 0. That's the system type. The KP, KV, and KA aren't, those are a byproduct. Once you know how many, what the system type is, or how many integrators, then you go over here and then you calculate what you need to. There's no point in calculating K sub B in this case, because K sub B is going to be equal to 0. Why calculate it? You know what it is. Same thing for the acceleration, going to be 0. Okay. So look at how many poles in your open loop transfer function at S equals 0, and that tells you the system type. When I looked at your labs, you know, there's a lot of like system type, it was a parabolic input. That's not the system type. The system type is a number of integrators. The input can be a parabolic, it can be a step, it can be a ramp. That doesn't mean that that's the system type. The system type is how the system was configured, not how you energize. So if you have feedback gain of unity, great. If not, that's okay too. Just remember that that's the actuating signal error, not the true steady state error. For this class, it's fine. You don't have to worry about it. Then we did something unique that I've never done before. We did some polar math, right? We went back to, I don't know, vector calculus or physics or pre-calculus, whenever you had that. And we showed you how to do magnitude and angle calculations using complex numbers. We said if we have magnitudes and angles, we can divide the magnitudes or multiply the magnitudes with polar math. And with the angle, we can multiply, we can add if they're in the numerator and subtract if they're in the denominator. So we found when we did polar math, it was a little bit easier to do the work. If we did in rectangular, we'd have to FOIL everything, but in polar, we can just multiply or divide and add or subtract. Simplifies things quite a bit. Then we saw how we could apply that to the root locus, which is 1 plus kg8 has to equal 0. And when we did that, we could solve for our magnitude of k being 1 over the magnitude of gh. Hopefully you see that the 1 has a magnitude of 1. And then our angle for that, if it's a valid point, has to be plus or minus 180. And we did that all with polar math. That was another example we did this morning with that practice example. So, we're kind of doing things a little bit different than how we stated it. But root locus start and end points, start at a pole, end at a zero. So always identify the finite poles and zeros on your pole zero map and start drawing anything you can. Identify on the real axis where the root locus exists, and then see, do I terminate? Do I start at a pole and do I end at a zero? If I'm good, then I don't have to do any work for that root loci. If I'm not good, then I have to see, do I have two poles or two zeros that are on the root locus axis? Do I have to calculate the break-in points or breakaway points? It's the same process, but I do it that way. And do I have any asymptotes? So that depends. If the order of the numerator is less than the order of the denominator, then I have some infinite zeros. But if they're the same, I don't have to do any asymptote work. So if n equals m, you don't have any asymptotes. So n minus m equals 0, no asymptotes. N minus m greater than 0, calculate your asymptotes. So you calculate your asymptotes, then you calculate your centroids or where the asymptotes begin, and you draw those on your diagram. Then, whoop, about that. Come on. Now we got to see if we got to do breakaway points or break-in points. It'd be either one, right? If we have two zeros on the real axis, we may have to break in. And we do that by solving this equation, taking the partial derivative minus 1 g over h and setting that equal to 0, and then solving for the valid break-in or breakaway points. Remember, valid, two criteria, has to be on the real axis, so you can't have a complex number with it. That's part one. And part two is it has to be where root locus or two root loci leave or enter the real axis. And then departure or arrival angles, that's if you start at complex conjugates or end at complex conjugates, you need to know the angle. So you do that. And here are the test questions. Given an open loop, a root locus plot, find GH. If I give you the S-plane, because what we've done is we have the S-plane plot, and we have this root locus. So go and tell me where are the points that meet certain design criteria. Design criteria is usually damping ratio, making sure that damping is less than a certain value, and a settling time. So a good one is zeta and omega sub n. And if you recall, can't remember the exact slide. This slide has all the details, right? So let's see. So zeta is a constant. So if we want our percent overshoot to be less than a certain value, we have to make sure our zeta stays below a certain value. If we want our settling time to be below a certain value, we have to be on that side, right? Those are the criteria that we have. So that's when you can look at your root locus and pick off points based on our values. This is also kind of an extension of when we looked at second order systems. We expanded it to this topic here. So let's go back to this. So if I have a block diagram, draw a locus. If I have another block diagram, give me the steady state errors. And if I want a desired ESS, I might have an adjustable gain that you want to make sure that that gain is either above or below a certain value so that your steady state error meets criteria. So we're using a lot of this stuff for design, not just analysis. And here's the table I would provide. It's just different now because the system type is going left to right. So again, you just look at the system type and you go to the left, right? And you can see, this is the error constant. The rest of these are 0. And then here is our steady state error. So you can see you can use it. So I created this table a couple years ago, and I just like the way it flows a little bit better. So I use this one. I included up to type 3, but we really don't need to worry about that. So you can put a line through those and not worry about those. Then I will include this. Don't worry about this. I gave you the partial of -1 over GH. That's the way that we could do it. This is another way to calculate it, but I replaced that with another one. That's it. Only 2 topics for the test. 2 major topics. Both in loop and utilize open loop transfer function. Both are, well, one is more focused on pole 0 maps. The steady state error one has some design characteristics, but not a ton. That's it. Questions? Yes, sir.
Yeah, so I guess if we give some condition time, if you be able to just go over like go into the practice problem.
Like this one, the one we just did.
Uh,
Why is this good?
Work out, I don't find an example that's not on the homework, because I don't want to.
Well, I just gave you this one right here. This is not on the homework, and it's a pretty detailed one with all the details.
Oh, so that's everything, so that covers all the topics that were.
For root locus,
Oh, okay.
the steady state error one is different. Yeah, this is all root locus stuff, right? This covers all except for angle of arrival and angle of departure. But we kind of do cover angle of arrival and angle of departure. So if we had a valid pole or 0, and we, that was a complex number, we would basically leave this as theta either A or theta D. So we have some that I worked out in the examples in the presentation, but I thought I would just do this one here and not confuse it with additional stuff. Just because it makes if I added some complex poles and zeros, we could do it, but I guess the math gets to be a lot and it can be confusing. So I tried not to go too crazy, but to get most of the major topics and still give you a little bit of how to calculate the angles. So hopefully you could send it the angle of approach or angle of departure.
All right.
So yeah, that was the purpose of the example, was to really give you a solid root locus example. And we could certainly come up with another one if people want another one, but it won't be as clean or as neat as this one that's all typed out.
Yeah, I think good. I think for I guess we would look at I think it's right. So, but
Okay.
I feel, but I think it goes.
Okay. How about TV land? Was this a good example? Would this give you enough detail, or do you feel like that's not enough?
Yeah, that was good. Thank you.
Okay. But does it feel like step by step, including MATLAB stuff to verify what we did on paper is pretty good?
Yeah, I think so.
Yeah, that seems sufficient. And there's also, other resources available too if we,
Okay.
need while studying.
Do you feel like this was a little bit, it's kind of going back over it, but hopefully kind of hitting things home, because now I can talk about it in a way where we can say, hey, let's use all these different things that we know and try to come up with it. Was that helpful?
Yeah, yes, it was.
Okay. All right, so questions, because that's pretty much, that's all that's going to be covered in this one. But again, you still have to understand second order systems to be able to equate terms and know how to use that. You still have to be able to understand pole 0 mapping. You still have to understand Ruth Hurwitz. So I'm not specifically testing you for that. It's just that stuff is relied on that you're going to be able to do that.
Well, pretty similar layout to your other exams where probably like 5 or 6 questions based on those example
Yep,
you gave us.
exactly. And you got almost 3 hours, so you should have plenty of time. And because I don't have lab in my other class, I'll be proctoring the exam, so I'll be here the entire time.
Awesome. Thank you.
Sure. And for those of you who want to take it remotely, you got to let me know earlier because probably by 11, because I have a meeting for peer committee that's tomorrow at 12. So normally I could do it at 12, but so I have a meeting from 12 to 1. I won't have time to get to it. So if you want to do it by 11. Okay, other questions?
I'll let you know if I have any while I'm studying, but I think
Okay.
I'm good for now.
Well, we have about 30 minutes left, so I know we started a couple minutes early, but I'm happy to answer questions or. I will say when I was looking over the homework and of the lab, a couple things. Remember the system type tells you the number of integrators. So a number of people didn't get that correct. And then the other thing too is your steady state error stuff works as long as the system is stable.
Yeah, I guess that's one thing I'm looking this over right now. Just trying to get it. I don't understand that, but I'm wondering if we have some time to spend a little bit, like going more focus into, I guess, the different types for steady state error.
Well, let's look at the lab. How about that? We can go through the lab. Okay, so here's the system. Hopefully that's legible. Let me see if I can zoom in a little bit. Copying from Simulink's not the best. So I'm going to use my open loop transfer function for steady state error. So the very first thing I do is my open loop transfer function. Let's see.
Share your screen.
Okay, thank you. Okay, thank you for that. Let's see if I can make the point a little smaller. Okay, so my open loop transfer function, GH, is 2K over S cubed plus 15S squared plus 50S, which is equal to 2K. And now I'm factoring a little bit because I want to find out the number of poles at S equals 0, S squared plus 15S plus 50. Okay, that's the first thing I do because now I recognize that's an S to the 1, which means this is a type 1 system. Okay. So for a type 1 system, if I go over to here, wrong one, sorry about that. For a type 1 system, stop it. All I have to worry about for a type 1 system is this. A type 1 system says my value of K, my value of K sub P is equal to infinity and K sub A is equal to 0. So all I have to do is calculate K sub B. For a type, for a step input, you can see that that's going to be equal to 0. And for a parabolic, it's going to be infinity. So the very first thing I do is, this is a unit step input. The stable or unstable is 1 plus, actually G over 1 plus GH is going to be equal to 2K over S cubed plus 15S squared plus 50S all over 1 plus 2K over S squared plus 15S squared plus 50. That's going to be equal to 2K over S cubed plus 15S squared plus 50S plus 2K, right? That's our closed loop transfer function. So the very first thing we do is we've got to check to see if it's a stable system with K equal 5. So I'm going to bring up MATLAB. And I'm going to type in the roots of 1, 15, 50, and 2 times K. And it's going to give me a burp, but that's okay. And I'll show why in a minute. Oops, forgot the parenthesis here. Doesn't like K. So now I'm going to define K equal 5. Now I'm going to do it again. And here are the roots. So the first thing is, are all the roots in the left-hand half plane? The answer is yes, they're all negative. So this is stable. And this is stable. Doesn't matter what the input is the system will be stable regardless. So it's bibo stable. If the input is bounded, the output is bounded. So stable. Now let's go back in and do the calculation with K equal 50. Are all the poles in the left-hand half plane? They're all negative. So, whoop, stable. And there's a 50 over here. Stable. Let's try the 500. That a stable system? No, we have 2 poles in the right-hand half plane. So, whoop. Where did it go? I didn't close it, did I? Did the lab close? Where did it go? Weird. Unstable. So stop. There's nothing to do. If it's an unstable system, I can't get a steady state error because the system is going to blow without bound, right? It can't keep up with anything. So I'm done with that one. So now I can fill in for a unit step. I look at my table. Where's Adobe? Really odd. Oh, here it is. Okay. So for a unit step, we know that the step input is 0. That's our predicted error. Our simulated error you're going to run through, and you should be able to do comment on that. The next thing we do is we can go to a ramp input, or a parabolic input, I should say. We know that our steady state error is going to be infinity. Now the only ones we need to calculate are these 2 for unit ramp. So for a unit ramp for 5, all we need to use is our K sub B. So K sub B is equal to S times G of S, GH. The limit, oops, sorry, not giving myself enough room. Yeah, let me do it on whiteboard, just because it writes a little bit better on whiteboard. Where's whiteboard? Oh, there it is. So K sub V is equal to the limit as S approaches 0, S times GH. Limit as S approaches 0. So now I'm going to plug in my GH. Wow, it's really weird. It's like it just, oh, there it is. Okay. So my GH transfer function is here. 2K, this value here. So 2K over S times S squared plus 15S plus 50. Cancel, cancel. And that equals 2K over 50. That's just dependent on that value of K. So for K equals 50 or 5, sorry, then KV equals 100 over 50. And for K equal to 550, K sub V is equal to 100 over 50, right? I have that right? No, this is 10. 2 times 5 is 10, not 100. So those are my values of K sub V. Now I gotta look at my steady state error. My steady state error is gonna be K over K sub B. It's a unit step, we're assuming, or a unit ramp, I should say. So for my ramp input, ESS is equal to 1 over K sub B. So over here, that's equal to 1 over 10 over 50. And over here, it's 1 over 100 over 50. That's equal to 5, and that's equal to 0.5. So this is equal to 5, and that's equal to 0.5. That's it. That's how to do the predicted errors. But the process is the same, right? I found the open loop transfer function. Then I went through and checked to see if it was stable based on a value of K. So I did it for all the different values of K for the gain. And I determined one was not stable. Once I did that, then I just looked at my table and said, all right, what do I need to calculate steady state errors for? And my position, acceleration, or velocity constants, I was able to pull that up, and then I could very quickly go to the table and get my results. Does that help, Tom?
Yeah, but would you go up a little bit?
Pardon?
Can you go up a little bit?
Sure.
Yeah.
Say when to stop.
Here. So I have a question. So I was thinking like if we have a block diagram like this and then there is a unity feedback, the transfer function that we have in the block, we only had to multiply it by K, so we have the open loop transfer function. So, oh, okay. I see now.
I'm not sure. Did you have a question? I don't want to.
Look, so I didn't get any concept correctly, but as I'm going through your work, so I see now what I was getting wrong.
Okay. I think most people where they struggle on this one was the concept of using the open loop gain or open loop transfer function. A lot of people use the closed loop, and that's why they were getting, incorrect results. What else?
But my question is let's take, for example, homework, the very recent one that we have.
Yep.
When you say you give an equation and then you say this is an open loop transfer function, so we have to use it as it is, right?
Yes.
All right.
Yeah, if I give you the open loop transfer function, I'm trying to simplify it. You can still get the closed loop transfer function, right? Especially if it's a unity feedback, because it's G over 1 plus GH. It wouldn't be so easy if it was not a unity feedback system. But if I'm just giving you the open loop transfer function, you don't have to worry if the system is stable or not. You can just assume that it is. I just added this one in lab because I wanted Pascal to kind of go over saying, oh, well, the system type would indicate that this is going to be a really small gain, but the system becomes unstable. So you remember how I said, you can continue to increase your value of K, but there's a realistic limit. And in this case, we saw that continuing to increase K, you think the error goes down, but then the system becomes unstable. So now you can no longer continue to increase K. You have to stop. That's why I put that one in there. Other questions? Nothing else? Feeling good, bad? Any other questions or comments in TV land?
No, I'm good.
You want to start new material?
No, not today.
Yeah, we really only have one more class to really present any new material. So we might do a little bit of stuff on Bodie plots. But we only have one class, so we don't have a lot of time. Because I always like to do the last class will be sort of a semester in review kind of discussion. But okay, well, if you don't have any questions and you don't want to cover new material, I'll end class here. So take care, everyone. I'll see you tomorrow. Good
See you
luck.
tomorrow.
Thank you.